All right, we're going to continue our look at some of those key ingredients for inferential statistics. We talked about probability. We introduced the idea of the normal curve last time. We're going to continue on with that, look at that today. But what we're going to be doing first is we're going to take up exam number 1. So exam number 1 has been graded. It has now been returned to you. So if you haven't already done this, you can sign into Canvas, go to the assignment tab. You can download your graded exam 1 Excel file. And what we're going to do right now is we're going to go through that, and I'm just going to go do a speed run of the exam and try to follow along. And hopefully, if you did get anything wrong in the exam, this will help you pinpoint exactly where it was that those errors occurred. You might recall we had our snowpocalypse a while back, and this course is very planned out, more so than any other course that I have. This course does not allow me to really squeeze content into a shortened time frame. Because of that, we are going to have to make up some of our classes that we missed, and the first one is going to be coming up tomorrow. So I just want everybody to be aware. I've picked the classes for the special online, snowpocalypse recovery classes. I picked the ones that have the least amount of post lecture practice that made sense in the order to come on a Friday. So this is just something that we need to do to catch up. So I'm going to record this and post it onto my YouTube channel, and then sometime before Tuesday's class, please watch this, because this is the introduction to hypothesis testing. This is where we're going to lay out the general idea of what we're going to be doing for the rest of the semester. So I'll post that sometime tomorrow. Please, sometime over the weekend, on Monday, maybe at the latest Tuesday morning, watch the class. Just kind of get a feel for it, because that is what we're going to be doing for the rest of the semester. Alrighty, a lot of stuff there. Okay, so now that we took care of that, let's talk about ninjas. And let's start on today's class. So for today's class, we're going to continue our look at the normal curve. And just to we kind of saw it there, we're going to start hypothesis testing next class. We're going to start looking at hypothesis testing, and that is going to be one of the first things that we're going to do in this course that is going to feel like the real work that psychology does. So this is going to be one of the first super cool things that we can do, where we can actually take a look at data from an experiment and say, what does it mean? We can actually take a look at the results of a treatment and say, does this generalize to the population? So we're so close to doing that ninja stuff that was promised, but we just still got one last little bit of stuff to do to make sure that we can get there, that we're prepared. So one last little piece of wax on, wax off before we start hypothesis testing next class. So as I mentioned again before, and I will remind you over and over again, the reason we do this is so that we can make psychology effective, so that we can generalize intelligently. So once again, without inferential statistics, if you had 14 autistic students that you were working with, and you found an intervention that increased the learning outcomes of those 14 students, without inferential statistics, that is where it ends. That is the end of it. That is the end of your impact. You have affected the lives of 14 people. Pretty good, right? Nothing to sneeze at. However, we want to be able to help hundreds of thousands of individuals. We want to be able to go beyond our sample and help the population of students. So we want to be able to help everybody, even people that weren't in our study. And again, it's very important that if we want to generalize from a sample to a population, that we have an objective strategy in order to do that, because human minds, human brains are horrible at generalizing. So you can make a lot of mistakes when you're generalizing. You could have a treatment that works and you fail to generalize to the population. You miss that your treatment is effective. That's bad because now people that could be helped are not going to be helped. On the flip side, you might have a treatment that doesn't work and you mistakenly think that it does and generalize that to the population. So that's even worse because now you have a treatment that is ineffective and all of a sudden you're telling people this is a great thing to do, this is a great treatment, even though it doesn't work. So we need a technique so that we can do that to the best of our ability. So we can go from a sample of, in this case, 14 individuals and intelligently generalize to that population. And as we're going to see today, that link between samples and populations goes through the normal curve. So we saw last time this idea of the normal curve, a frequency distribution. This is a unit normal curve where it has a mean of 0 and a standard deviation of 1. This is a normal curve of z-scores. But we saw that normal curves occur when a single score, in this case a single position in this toy, is determined by multiple factors, multiple independent occurrences. So where you end up in this toy, in this position, depends upon how many times hitting a peg made you go left, how many times hitting a peg made you go right. And because of that, they fall in that normal pattern where there's a higher proportion in the middle and fewer lower frequencies on the extreme ends. All right, so today we're going to extend that idea, and we're going to talk about samples and populations. We're going to talk about the distribution of sample means. So this is a tricky concept. It's going to take some mental effort to try to hold on to it. But we're going to talk about the distribution of sample means, and then we're going to end with the central limit theorem, what I like to call the mathemagic that allows everything else to happen. All right, samples and populations. Samples is the data that we have access to. We only ever really have access to a sample of data. We only really ever have access to a sample of individuals, and yet we want to know something about the entire population, right? So we have in that educational example, we have 14 autistic children in our classroom. And we want to say something, though, not just about those 14. We want to say something about the population of autistic children. So samples are oftentimes used to estimate population parameters, things about the population. So, for example, we can measure a sample and measure their mean IQ in order to predict what's the population's mean IQ, using that sample to predict the population. So if we have a population here, most of the time, population parameters are unknown. So this is especially true in psychology where we are dealing with new populations all the time. So if you want to know the average intelligence of children between the age of 10 and 18 who use at least 40 hours of social media a week, nobody's ever looked at that population. Nobody's got data on that population. That was not part of the U.S. Census at any point. Populations are usually unknown. But what we can do is we can start to take people from that population. So we can take this individual, and we can take this individual, and we can take this individual, and this person here, and we can say, all right, we're going to take a whole bunch of people, and we're going to get a sample. And that sample, which we see here, which has its own frequency distribution, that sample has a known mean because we can go out and we can measure it. If I want to know the IQ of a sample, I can give those 5 individuals an IQ test and say, fill this out. And then I can say, all right, I have your IQ scores, I can calculate the mean. I know the standard deviation because I can calculate it because I have access to those raw scores. So we use that sample to estimate that population. Now, this is an example where the sample correctly estimates, for example, the population mean, right? So the mean of the sample here lines up with the population mean. However, one of the key sort of challenges is that we don't always know where our sample comes from. Remember, we don't know about this population. We don't know what the population distribution looks like. So we don't know if our sample came from those positions in the distribution or if they came from these positions. So maybe this was the first person that ended up in our sample. Maybe this was person number 2, subject number 3, subject number 4, subject number 5. Maybe this is where our sample came from in our population. And notice now that when we measure the sample, we measure the mean, for example. In this case, we are vastly underestimating the mean of the population. The mean of the sample is right here. The mean of the population is right about there. So in this case, we just happened to choose 5 people that had low scores in this population, and those 5 people gave us an incorrect view, an incorrect estimate of the mean of that population. And just to make matters doubly worse, we might have gotten 5 people on the other side. So maybe our sample of 5 included this individual, and this person, and this person, and this person here, and this person here. In which case, this is our sample. This is all we know, right? Again, we don't know what the population is. We just have these 5 individuals. We measure their IQs, for example, take the average. We know what that average is. We try to use it to estimate the population, but in this case, we're vastly overestimating what that population parameter is. All right. So samples are used to estimate population parameters. It's just the way that we do it. We take a sample, we estimate the population. But the challenge is, or the problem is that different samples from the same population will have a different sample mean, right? So when you take a sample from a population and you measure their average IQ, for example, the population mean is 100. But if you take a sample of 5 individuals, their average IQ might be 114. The next sample of 5 individuals might have an average IQ of 97. The next sample of 5 individuals might have an average IQ of 120. Every sample of 5 individuals is going to have a different average IQ. And most of those sample means are not going to equal the population mean. It's very rare that you will get it exactly equal to the population mean. And that's what's referred to as sampling error, the amount of error between a sample statistic and its corresponding population parameter. So sampling error is basically how much did you overestimate your population parameter based on your sample, or how much did you underestimate your population parameter based on your sample. So this situation here, the mean would have a very low sampling error. This situation here, the mean would have a very high sampling error. All right, so far so good? Okay. So when we take samples from the population, we never know if we're dealing with this situation here or if we're dealing with this situation here, right? We can't tell if we got 5 people from our mystery population from the center of the distribution, or did we get 5 people in our mystery population from the extremes of the distribution. So we can't tell. However, we do know something. We do know that some of these samples are more likely than others. We do know that some samples, some sample means from the population, samples that'll give you that sample mean, some of those are very likely and some of them are highly unlikely. They all have different probabilities. So the best way to illustrate this, or one way to illustrate this, is let's say that you were going into the IQ Olympics. Let's say that there was this annual test of intelligence where teams would be formed and they would go and compete in the IQ Olympics. And you are going to be assigned a random sample of 5 individuals from the population, right? 5 individuals from the 7 billion on this planet. You're going to be assigned 5 individuals from that population. Let's make it a little simpler. Let's keep it the 7 billion. So 7 billion people on this planet, you're going to get 5 individuals. So they start randomly pulling names out of a hat, really big hat, but they're randomly pulling names. And these happen to be the 5 individuals that are on your team. So you would take a look at these individuals and you would say, all right, looks like kind of typical, right? I didn't get lucky. I didn't get unlucky. They don't look massively intelligent. They don't look massively unintelligent. This is kind of like, I don't feel like it's kind of typical. I don't feel like I got unlucky or I don't feel like I got lucky. This kind of seems like a team that has a high probability of occurring. All right, so we have this team that has a high probability of occurring. That is the team from the middle of the sample, right? So this individual here, she is this individual here, right? IQ slightly lower than average, but not very low, right? She was able to, whoops, spoiler alert. She was able to, land a job. This guy over here is this dot right there. This individual here is this dot right there. So she's got an average IQ. And then we got this individual here, and he has an above average IQ. And then you lucked out with, whoops, not him, one individual here. And she has, a higher IQ than everybody else, right? So you got some low IQ individuals. You got some high IQ individuals. Seems kind of typical of what you would get randomly, right? Typical seems like this has a high probability of occurring. Now, let's say that your friend is also entering this IQ Olympics. And you ask your friend and you say, oh, did you enter? And they're like, yeah, I entered. And you're like, did you get your randomly assigned 5 individuals? And they're like, yeah, I got my randomly assigned 5 individuals. And they're like, well, that's great. Well, who were they? And they're like, well, you're not going to believe this, but the first guy was Bill Gates. And you're like, oh my gosh, how lucky is that, right? Bill Gates, part of the population. Bill Gates, one of the names in the hat, right? But pulling Bill Gates seems rather unlikely, seems rather lucky. So if your friend told you, yeah, my first teammate is Bill Gates, randomly assigned, you'd be like, whoa, that is lucky. And my second teammate, Neil deGrasse Tyson, and you'd be like, oh my gosh, too good to be true. Like who could believe, seems very unlikely. And my third teammate, you're not going to believe this, Bill Nye the Science Guy. And you're like, really, Bill Nye the Science Guy? Are you kidding me? How lucky were you that you got 3 people from the extreme end? And he's like, it doesn't even end there. My next one, Marilyn Vos Savant, the highest recorded IQ in the history of the world, while Guinness was still recording those. And you're like, oh my goodness. And then my last one, I got Ruth Lawrence. And you might be sitting there going, oh, well, who's Ruth Lawrence? Well, she's a mathematician. This was her when she graduated Oxford at 13, I believe, with her math degree before completing her PhD by 17, I think it was. Anyways, very, very highly intelligent person. So what do we got here? We got Bill Gates, we got Neil deGrasse Tyson, we got Bill Nye, we got Ruth Lawrence, and then we got Marilyn Vos Savant. We got people from the extreme. And it seems mind-bogglingly unlikely that they would occur, right? It would seem that this situation here is much less likely than this situation here. And you're absolutely correct, right? This team is massively unlikely. And we're going to see that we can figure out just how unlikely that team is using some of the principles that we're going to introduce. So while we don't know which sample or from where in the population our sample came from, we do know that different samples have different probabilities. Samples that take from the center have a higher probability. Samples that take from the edges, they have lower probabilities. All right, make sense so far? All right, the challenge. How can we tell what is the probability of selecting a sample with specific characteristics from a population? So we just said this one has a high probability. This one has a low probability. But how can we actually put a number on that? How can we actually calculate that out? That is, what is the probability of getting a particular sample from a population? I.e., what is the probability? What is the proportion? What is the proportion of a distribution? So this is going to be the first part where you're going to really see that it pays off by thinking of probabilities as a proportion of a distribution because that's exactly what we're going to use to figure out how likely is this sample versus how likely is this sample. All right. So we're looking for the probability of a particular sample. And probability equals proportion of a distribution. And this is where we need to kind of hold on tight to our cognitive processes here and just kind of hang on for dear life. So we want to find out what's the probability of a particular sample. Probability equals a proportion of a distribution. Proportion of the thing that you're looking for the probability of. So we need to have, if we're looking for the probability of a particular sample, we need a distribution of samples. We're looking for the probability of a single sample. We need to find a distribution of samples. And that's where we come across the idea of the distribution of sample means. So the distribution of sample means, it's exactly what it says on the tin. It is a distribution of a whole bunch of different sample means. So it's a collection of sample means from all the possible random samples of a particular size that can be obtained from a population. It's literally what you would get if you said to yourself, all right, I'm going to take samples that are 5 individuals large, right? So my size of my samples is going to be 5. And I am going to take all of the samples that I can, and I am going to calculate their means, right? So I'm going to take every sample that I can, and I'm going to calculate that sample mean. So you call in 5 people. You take your first sample. You say, here's an IQ test. Let's say that we want to do average IQ tests. You have sample number 1, first 5 people. You say, here's your IQ test. They fill it out. You take their scores. You calculate the average. They have an average IQ of 109.5. You then say, get out of here. And the next 5 people come in. And you say, all right, you guys are number 2. Here's your IQ test. Take the test. Let me see your scores. I'll take the average, 89.6. You then say, get out of here. Bring in the next 5 people. Sample number 3. IQ scores. They take the test. You record the scores. Take the average, 115.2. You then say, get out of here. And you keep doing this. You do this, and this is the part that's kind of hard to wrap your brain around. You do this for all the possible random samples of a particular size that can be obtained from a population. So at some point, you're going to have sample number 10,487,352,451. And you're going to say, here's your 5 IQ tests. So tired. Take them. I'm going to add them all up. All right, here's your mean, 97.9. Get out of here. Next 5 people come in. All right, so it's a lot of samples. But importantly, when you're done, you're going to have the means for a whole bunch of samples, and then you're going to take those raw scores and you're going to put them into a distribution, and that is the distribution of sample means. All right, so that's one example. Let's take a look at another, just to kind of drive this home. So, distribution of sample means, let's take it out of the world and into dice rolls, something that we can mentally handle a little bit easier. So, if you were to take a look at 6-sided dice, and you were to take a look at the population of dice rolls, i.e., every single dice roll that was ever done in the history of mankind, and you went through and you recorded all of those dice rolls. This person rolled a 6, this person rolled a 5, this person rolled a 4, and you were to take the mean, you would find out for fair dice that the mean of those dice rolls is 3.5. The population mean of every single dice roll ever in the history of man is 3.5. And this is the frequency distribution for that population of dice rolls. And you can see that rolling a 1 is has the same frequency as rolling a 2, as rolling a 3, 4, 5, and 6. Center of that distribution, the mean is 3.5. That's where we get the 3.5. That's a population. What about a sample? Well, let's say that you're starting with a sample of single dice rolls, right? So we are starting with a sample of just one dice, right? So you start off with a sample of single dice rolls, and you roll that first, you roll your dice, and you take a look at what comes up, and you're like, okay, that's a 5. The mean of a single dice roll will be 5 divided by the number of rolls, which is 1. 5 divided by 1, you get a mean of 5. You roll it again, you get a 3. You roll it again, you get a 4. You roll it again, you roll it for the 4th time, you get a 1. And you keep doing this for a sample, for every possible sample of one dice roll. And what you're going to find is your mean of your sample means, right? So if you take the mean of all these sample means, it's going to be 3.5. So first thing to notice, the mean of this distribution of sample means matches your population. Pretty good so far. Next thing to notice is that if we were to plot this on a frequency distribution, let's finish it off because it's easy. 2, and then your 6 dice roll, you get a 6. If we were to take every single possible mean from the sample of dice rolls, and we were plot it in a frequency distribution, that would be the distribution right there, and that is your distribution of sample means. So every single point, every single occurrence, every single person living in these apartment buildings is the mean of a sample. And that's the key thing to remember. It's now gone from the point where we're looking at a population distribution, which is an apartment building where people are living alone. Now we're looking at a distribution of sample means, which is an apartment building that has, in this case, or in the previous example, 5 people living in each apartment, however large your sample is. All right, so this really becomes apparent when we up the ante and we take a sample of 2 dice rolls. So now what we're doing is we're having a sample of 2 dice rolls. So we take 2 dice, we roll it. If 2 5s come up, we're like, what's the average of that? 5 plus 5 is 10 divided by 2. We get an average of 5. We roll it again. We get a 6 and a 1. Average of 3.5. We roll it again. We get a 1 and a 2. Average of 1.5. We roll it again. We get a 4 and a 2. Average of 3. We roll it again. We keep doing this for every possible combination of 2 dice rolls, and then we take this distribution, these scores, put these means into a distribution, and your distribution of sample means is going to look like this. We'll have the same mean as your population, but now it looks like this. And if you continue to do this, you do it now with a sample of 3 dice rolls. And again, you take 3 dice, you roll them, you add up the scores, you take the average. Take 3 dice, roll them, add up the scores, take the average. Do that for every combination, every possible sample of 3 dice rolls. You're going to find out that your mean of your distribution of sample means, right? So you take all the means from those 3 dice rolls, put them in a distribution. It's going to look like this. And the mean is still 3.5. Notice the mean is still lining up with that population mean. All right, and we'll just keep this going a couple more times. We got 4 dice rolls. Once again, same mean for your distribution of sample means. Once again, your distribution of sample means plotted here. And then finally, for 5 dice rolls, we have the same mean for our distribution of sample means. And we have our sampling distribution, our distribution of sample means. And once again, it looks like this for 5 dice rolls. Starting to look a little familiar. Starting to look like that normal curve that we've seen previously. All right, so that's one way to find out your distribution of sample means. You take a sample, you measure it, you throw it back. You take another sample, you measure it, you throw it back. You take another sample, you measure it, you throw it back. You do this until you've exhausted every possible sample.
Mm-hmm. Is that just a general rule for distribution of sample
Yes, it will be. It's a mathematical rule, which is one of the reasons we use it. Is it matches up with that population mean. So one way to do this is what we did to create these graphs. You take every possible sample, but nobody does that. Usually you only have access to one sample. I have never known a psychologist in my life that has taken a sample of 20 people for an experiment and then said, all right, I'm done with these 20, throw them out, give me another 20. All right, I'm done with that 20, throw them out, give me another 20. How many times are you going to do this? Oh, I don't know, 40 billion times until I get every sample from the population. Nobody does that. We wouldn't have psychology. Usually you only have the one sample, right? Oh, I ran 36 subjects. I have one sample. So what do we do? How do we get this distribution of sample means? Well, this is where we're going to end our look today. And it has to do with the central limit theorem. So the central limit theorem is how we figure out this distribution of sample means. And it is very powerful. It is what makes psychology possible, and I'll show you that in just a moment. But this is what it says. It says that for any population with a mean of mu and a standard deviation of sigma, what that means is any population with a mean of mu and a standard deviation of sigma, the distribution of sample means, that new distribution that we were looking at, from a sample size of n, for a certain sample size, right? Sample size of 5, if you got 5, sample size of 20, if you have 20, whatever your sample size is, it will have a mean, this distribution of sample means will have a mean that is equal to your population distribution and a standard deviation that is related to your population standard deviation. So it's not equal, but it is the population standard deviation divided by the square root of the size of your sample. Why square root? Don't ask me. That's grad school level statistical stuff, not beyond the scope of this course. But just know that the important thing is it's related to it. It's the standard deviation of the population divided by the square root of the size of your sample. And then lastly, it will approach a normal distribution as the size of your sample approaches infinity. And that's one of the big key things. And what that does is that basically opens up statistics, because for any population, your distribution of sample means, you might not know what your population looks like. You might not know your population distribution, but your distribution of sample means, and we're going to see how to use this in the next coming weeks, but your distribution of sample means will be approximately normal. And what that means is that all the work that we did in the prior week, where we were learning how to use that normal distribution, all of those going from a raw score to a percentage, all of that comes into play because whenever you take a sample, which is almost always in psychology, you end up with a normal distribution for your distribution of sample means. And that opens up everything in psychology. So to kind of drive this home, let's take a look at some visual examples. So here's the population distribution right here. This is usually unknown. Here's the distribution of sample means. And we're going to take a look at what it looks like for different sample sizes. The first thing to notice is that when you have a sample size of 1, right, one individual in your sample, your distribution of sample means looks exactly like your population distribution. So what this tells you is that sample sizes of 1 are typically useless. Nobody ever says, how many subjects am I going to use for my experiment? 1. 1 sounds good. You can't do stats on 1. If you ever read a case study, they don't do inferential statistics on case studies. This is why, because we don't know what this looks like. But as soon as we go to a sample size of 2, that's your distribution of sample means, different from your population. Now that we got 2 people living in each apartment, more people live in the center, fewer people live in the extremes. Sample size of 3, sample size of 4, sample size of 5. Even as low as 5, this thing starts to look like a normal curve. What if this is your population distribution? Well, sample size of 1. There's your distribution of sample means. Once again, useless, right? Can't do stats with it. But look at your distribution of sample means. Central limit theorem says as your sample size increases, it's going to start looking more and more normal. There's a sample size of 2, distribution of sample means. Sample size of 3, sample size of 4. There's your sample size of 5. Notice, we only have 5. That's a very small sample size. It's already looking normal. What about this distribution over here, where there is large portions of the population that don't score in that particular score? Distribution of sample means, sample size of 1, looks exactly like the population, no help there. Distribution of sample means for a sample size of 2, sample size of 3, sample size of 4, sample size of 5. And you can see that even with this bizarro population distribution, once you go to a sample size of 5, we're already getting a sample distribution, a distribution of sample means that is looking like a normal curve. We are almost to the point where we can open up appendix number 1 and start doing some real statistical work. So again, central limit theorem says that for any population is going to have a mean, any population is going to have a standard deviation. Your distribution of sample means from for a certain sample size, so it doesn't matter what sample size you use. You can use a sample size of 20, 30, 15, whatever you want. It's going to have, your distribution of sample means will have a mean that's equal to your population, a standard deviation that is related to your population, and importantly, it'll approach a normal distribution as your size of your sample approaches, infinity. So this, again, is the key thing that allows us to do stats in psychology. One of the big things is that it approaches a normal distribution. So we only have to figure out that one distribution and how to use that one distribution. That's all we need to work with. And the other key thing is that this is true for any population. And that is important because that opens up psychology. So if you are interested in the effects or the amount of depression in single fathers with children under 5 years of age, who has the population data on that? Nobody. Who knows what that distribution looks like for the population? Nobody. But as soon as you start taking a sample, as soon as you interview 20 fathers, 20 single parents of children under 5, that sample comes from a normally distributed sample of population means. If you take a look at the amount of, let's think here, the similarities between gay couples, right? If you take a look at the similarities between gay couples in terms of physical similarities, who knows what those scores are on the population, right? Who knows what that might be? But as soon as you take a sample of 40 gay couples, you know that their similarity scores are going to be in their sample mean. That is part of a normal distribution. And it works, again, for any population. So I remember in one of the advanced labs that I was supervising, a student of mine came up to me and she said, can I do, what were they called? Can I do my study on, I believe it was connected Bohemians. She goes, I want to do a study on connected Bohemians. And I was like, I have no idea what a connected Bohemian is, but I guarantee you, yes, you can do your study on that population. Because the central limit theory says, for any population, you can do stats on it because the sampling distribution will approach a normal curve. So it was actually from the Claritas prism. This is a geodemographic segments in the United States where they can split, advertisers and marketers often use this, they can split people up into different demographics. And she specifically, it was connected Bohemians. She specifically wanted to study this population here. She wanted to study the mix of young singles, couples, and families ranging from students to professionals, all having one thing in common, being tech savvy. They are always early adopters of the latest and greatest things. I don't know when this population was brought into being. I don't know when this population was identified. And I have no idea about anything. She wanted to do color perception. I don't know what their color perception abilities are. But I do know that once you take a sample of connected Bohemians, regardless what their population distribution looks like, as soon as you take a sample, according to the central limit theorem, their distribution of sample means is going to be a normal curve. So, to wrap this up today, the central limit theorem is what allows us to figure out the distribution of sample means. It's what allows us to go to the unit normal distribution table and use those z-scores. It's basically what allows us to do psychology. And as we're going to see, it's the backbone of being able to make those intelligent generalizations from a sample to a population. All right, so one last thing to wrap this up. So going forward, it's going to take a little bit of practice. It's going to take a little bit of mental determination. Don't let yourself slide on this. Keep in mind, you might want to have this slide somewhere handy. We are now dealing with 3 separate distributions. And it's very important to keep in your mind clear distinctions between those distributions. So we have our population distribution. This is the one we've seen before. This is your population distribution. This is your individuals living in their apartments, right? So individuals living there in their apartments, that's your population distribution. We also have a sample distribution. If you take a sample, if you take a whole bunch of people from a population, you measure them, they form their own distribution. And different samples will form different sample distributions. And then if you take those sample means and you put them into a distribution, you get a distribution of sample means. And this is a new apartment complex where sample-sized people live together in the same apartment, so it's a different distribution. So keep these 3 very, very separate. Population distribution, sample distribution, and distribution of sample means. Whenever you come across those, take a moment, think about, practice that mental determination, remember which one you're talking about. All right, so that is it for today. So you're ready to go and work on homework assignment number 7, chapter 4, part 2. That is going to be due Monday, February 25th by midnight. And then, as always, work on that study plan. For anybody that does not get a perfect score on your pretest, you can up your score by completing the mastery points on that My Stat Lab study plan. All right, so keep this in mind again, keep that mental determination. We are going to have to, again, just to remind you, do that special online class on Introduction to Hypothesis Testing. I chose it because it's sort of our welcome to the hypothesis testing world. So I'm going to post that sometime tomorrow. Make sure that you watch it before class on Tuesday, because the way that this course works, every lecture builds on every other one. So please, when you come to Tuesday's lecture, make sure that you've watched that previous one, because I'm going to continue on with the program that I've developed, which assumes that you've seen that previous one. Other than that, we are done for today. Took it to the limit, but that is it. So enjoy your weekend. Make sure that you check out that special online lecture sometime before our next class, and I'll see you all next time.